So, I am going to basically talk about the implementation details of our EdgeRIC with srsRAN 5G. Please do get in touch with us to access our code base. Hopefully, we will be open sourcing it over the weekend or over a week or so, but you can always access our entire implementation details on our website. So, just to recapitulate the EdgeRIC overview, we are basically operating at the real time timescale, which is 1 millisecond timescale. What we call as the equivalent of R apps and X apps running in real time is what we refer to as micro apps, mostly motivated by the fact that it requires microsecond timescale of inference. What is the philosophy behind EdgeRIC is basically we want unprecedented optimizations in the Phi, MAC and RLC network functionalities of the RAN, and also with a flavor of application in aware decisions in these network functions. And EdgeRIC is co-located with the srsRAN as of our current implementation. What we are targeting is basically each slot by slot action, that is we want to be able to give a decision for every slot or every TTI as per the standard name. So, what is the exact EdgeRIC architecture? You have the srsRAN, as of today we have the srsRAN code base written completely in systems language C, C++. Our philosophy for EdgeRIC is to actually be able to open up APIs to the community in general to develop a bunch of machine learning algorithms which can be completely written in Python and deploy your micro apps or ML based optimizations for network functions, write it in Python, deploy it with the RAN stack. So, what we have done for the community is that we have written our own EdgeRIC class, which we call as the RTE2 agent, which is integrated inside the srsRAN code base. Our current implementation, the message exchanges between EdgeRIC and the srsRAN occurs over the ZMQ message passing library. What we have is the RTE2 agent collects all the metrics, it publishes over the TTI, it publishes over a ZMQ pub socket. Our real time variant of the E2 interface is what we refer to as the RTE2 interface. The RTE2 report is all the metrics collected over the TTI that the RAN sends over to EdgeRIC. The message schemas that we have tried to define for the RTE2 interface is based out of Google's protobuf buffers. So, the entire schema is written in protobuf basically. So, what happens on the EdgeRIC side is it receives the RTE2 report as a ZMQ sub socket, and it does the decoding of the entire metrics that comes over the protobuf, and it computes a policy on the received metrics and again sends it back as a publisher socket, which we refer to again as the RTE2 policy, which is basically the decisions that the RAN needs to take for the next TTI. And on the other side, the RTE2 agent in the RAN has this subscribing socket, which collects the policy decisions and actually applies it in that particular TTI. What is very essential for our operation to maintain this TTI by TTI sync is that we always ensure that our RAN index is always equal to the RIC index. Every time a message is sent out of EdgeRIC, the RIC index also increments by 1, and we have to ensure that the state and action are always TTI by TTI synced. In case one of them is lagging behind, we try to drop off the messages from the queue just to keep both these entities in the same time sync. So, the key to real timeness is basically the TTI by TTI synchronization, which we try to incorporate in both our metrics and the policy report messages. What is the schema of our RTE2 report? This is our current implementation. What it contains is we send data on a per UE basis. So, for each UE, we identify the UE by its RNTI, which is the radio network temporary ID. And for each UE, as of today, what we put out is basically the downlink backlog buffer, the uplink backlog buffer, the SNR, CQI, the bytes transmitted, the bytes received, and also basically the buffers, the bytes transmitted, and the channel qualities. And at the same time, you also as part of the message, as you can see, the RIC ID and the RAN ID are also part of your metrics message. These are all the metrics which is currently supported as part of our code base. And this is what the protobuf schema actually looks like. Similarly, okay, for the I can actually run it in real time, but yeah, this is basically the helper function which is written on the EdgeRIC side, which is like a small Python code to do the decoding of the RTE2 report. And what does the RTE2 report basically looks like is that is as follows. This is basically from a snippet taken from a 2UE system where I can see what is the TTI number, and as per the UE metrics you can see the two identifiers here are 17921 and 17922, which are your RNTIs, and corresponding to both the RNTIs you are getting all the associated UE metrics for the TTI number 578000. Currently supported metrics is metrics per UE per slot is what our code base supports, and we also have a bunch of physical layer capabilities which would be presented in the talk right after this. We are also able to receive the channel estimates per subcarrier per antenna. On the other side, on the control side, which is the messages going from EdgeRIC to the RAN, which we call as the RTE2 policy. What does the structure of the message look like? For each micro app, you have the micro app 1 control message, and at the end of the message is again the RIC ID and the RAN ID. And what is the structure of each of these micro app control messages? It is the identifier, which the UE identifier, and the corresponding action for that particular UE, and so on. Again, the way the protobuf schema is defined is as follows. This is all part of the code base right now. And main idea for our real time control is that we send an action to be taken per UE for that particular time slot. That is the basic idea for our RTE2 policy. Again, the helper function for sending these, for example, on here I have shown MCS sending policy where we send the MCSs for each of the UEs. And how does the typical RTE2 policy look like? We send the RAN index first, that is, this is the action to be taken for that particular TTI, and again the MCSs are defined over here. For example, the RNTI 17921 gets MCS of 28 and RNTI of 17922 gets MCS of 15. So, this is the basic RTE2 policy. So, our currently supported control actions is basically the scheduling decisions per UE. Scheduling decisions here we mean how many PRBs that I should be allocating to each of the UEs in that particular TTI. Again, MCS decisions per UE, that is what is the MCS that should be used for transmitting to that particular UE. For physical layer control, we are able to control the MIMO precoding matrix as well. Again, this would be elaborated in the talk right after this. Now, I will briefly go over how we are achieving the scheduling control, that is we made a slight modification to the srsRAN code base to implement this weight based abstraction of control. The main idea of weight based abstraction of control is that you are able to implement any kind of a scheduling policy with these so-called notion of weights. So, what is this weight based control? Is basically you have multiple applications which is connected to your RAN stack. The question is how many resource blocks should I actually allocate to any of these users in a particular slot, and we send a weight which is a number between 0 and 1 for each UE. The way RAN allocates number of PRBs is basically the weight times the total number of PRBs, which would give the actual number of PRBs to allocate to the particular UE. So, this is an example of sending a fixed weight. I would like to go over some demos for this. Oh, okay. Sorry.
This might also be it.
Yep, escape again.
Escape again.
Yep.
There's two PowerPoint.
No, too far.
Now you can.
Oh, sorry. Okay, yeah. What is coming now? Oh, this is bad. My remote thing is not working. This is sad.
There's going to be a lot going on, so it's just
Okay, I'll just continue with my presentation. Yeah, sorry about that. I might show it at the end of the talk maybe then. Basically fixed weights, as you can see, we are trying to give 0.7 to one of the RNTIs and 0.3 to the RNTIs. This is pretty visible in the G0B console when we, I'll try to run it at the end of the talk maybe. Similarly, for MCS control, you are able to send what is the MCS per UE. So here you can see we were able to, this was all supposed to be part of the demo, really sorry about that. So we are sending MCS of 20 and an MCS of 10 for each of the two RNTIs here, but this could be based on any of the policies that you actually take for your MCS or your scheduling decisions. So here's the overview of our current EdgeRIC architecture. You have a ZMQ publishing socket which goes from the RAN to EdgeRIC. And the message format here is the metrics.protobuf buffer. And for the control side of things, we actually open up multiple publishing ZMQ publishing ports from EdgeRIC to carry the control messages for each of these network functionalities. So this is basically the current EdgeRIC architecture available today. We are thinking of other methods as well, like shared memory and so on, to do the message exchanges between the RAN process and the EdgeRIC process. So what is our basic implementation is of the RT-E2 agent in srsRAN. We have actually defined this EdgeRIC class inside the srsRAN code base, and this class basically has all the getter and the setter functions. The getter functions is for getting all the metrics from the RAN measurements over that TTI, which is then packaged into the protobuf schema and so sent over for that particular TTI. And again, the setter functions does the exact opposite of this, which collects the stuff coming in from EdgeRIC and then sets that particular action for the corresponding network functionalities, so that the action can take place for that next TTI. Now, how to write micro apps with this abstraction with our EdgeRIC class? All you have to do is first, in your Python program, you just import the EdgeRIC messenger. You retrieve the RAN state by using the getMetrics function of our EdgeRIC messenger, and then you have all the metrics for each of the UEs available to you. Decode it and then compute some policy based on the states of each of the users for that particular slot. You have a policy, send the action back over via the EdgeRIC messenger, which will do all the job of your packaging up your control policy message over the protobuf schema and then send it back to the EdgeRIC's RT2 agent, which will then pick it up and apply the corresponding action to the right network function, functions. So now I'll go over some of the mu apps that we actually deployed, and those were in demo over the last 2 days, and how we optimize network policies. I'll go over how we did the reinforcement learning training for the throughput maximization, and also the application aware network scheduler to improve the video quality of experience. The first micro app is on max scheduling. Again, the control policy is the weight vector for each of the UEs. Basically, how many resource block groups should I allocate in that particular slot. The metrics that we use for our inference is the CQI and the backlog buffer, that is the channel quality, and the downlink queue or the downlink pending data waiting to be sent to each of the users for that particular slot. And our main goal or philosophy is to maximize the overall system throughput. So implementing scheduler policies, this is the main function of the scheduling micro app. And the way we set the scheduling algorithms is via this Redis server. So EdgeRIC maintains a Redis database, and we can choose our scheduling policies via the Redis server. And as of today, we support max weight, proportional fairness, max CQI, round robin, as well as our custom reinforcement learning based scheduling that can be implemented with EdgeRIC. And how did we train our policy? As was spoken about in the talk, just before mine. We treat the RAN as our environment, which sends all the metrics for that particular TTI. We can also get a bunch of metrics from the application servers themselves, which comes to EdgeRIC. So the state comes from the environment to EdgeRIC. EdgeRIC can be integrated with the Open AI Gym class interface, which allows you to do off-the-shelf RL training of RL models, and then you send the corresponding action back, and the model continuously trains by collecting samples from this environment and learning how to maximize the reward function. So in our case, our objective was to maximize the system throughput, and the state that we looked at was basically the CQI and the backlog buffers of each of the UEs, and these are our corresponding specifications that we have. The state is the backlog buffer and the CQI of each of the users. The action here was the weight of each UE, that is, or the number of resource blocks to actually allocate to each of the users, and the reward for our agent here was the total system throughput achieved by taking that particular action. So how was the training done? It was done on our Tiny Twin, which is our module for AI training, which is nothing but basically running all these software UEs in the ZMQ mode of operation. And for the channel, what we did is actually put in our own CQI traces that were collected over a bunch of scenarios, mobility scenarios from over-the-air experiments. And every time the SRS UE ran, it basically runs with the particular trace file given when it started. So so our Tiny Twin basically a channel trace driven network bring up, and by which we can emulate all kinds of wireless scenarios. So we have the RTE2 agent, and this is our entire module for our digital twin AI training. EdgeRIC simply receives the samples from this environment and sends actions back, and the RL agent learns in the background based on our throughput, based on the reward function that has been specified. So yeah, these are all the real world traces that we actually evaluated on. We have a bunch of mobile UEs as shown here, and yeah, as we can see that the real world channel changes really fast in about less than 5 milliseconds, and that's the reason why we are actually looking at all these real time control and optimization policies for the network functions. Training policies with Tiny Twin, these are some of the training curves that we observed with the specific RL, with these RL specifications, state, action, reward, where we are basically trying to maximize the system throughput. As you can see, as the agent trains, it trains in about 50 or 60 iterations. It's able to reach to a convergence point of achieving the maximum system capacity that the system can provide. Training the RL agent, code structure, we have this RL agent, which basically we have an agent that collects samples from the environment. How does the agent collect samples? We have this EdgeRIC.getMetrics policy that collects these samples. Get metrics using our EdgeRIC messenger. This is all the Python side of code. You extract all the stuff from the schema that you actually receive via the EdgeRIC messenger, and then compute some policy and send the scheduling action back. And you keep doing this over and again, and that's how the agent keeps learning over time. Similarly, we also trained another RL agent to optimize the video quality of experience. So here our target scenario was real world content streaming, and we wanted, our objective was to reduce the stall duration or the rebuffering time of the video player. So we had 2 video streaming agents, and we also had like some background system loader which is running like a very high throughput application in the background, and we wanted to see what happens to the scheduling agent if we are able to give in some kind of an application context in the training of the thing. So this is our RL specification. Again, now the state incorporates the network metrics, which is again the backlog buffer and the CQI, and the additional metric here is the media buffer. Media buffer meaning the playout buffer length of the video streaming UEs, that is the amount of buffer remaining for video playout at the client. So the reward here is basically we are trying to give a really high negative reward at any time when there is when the buffer is actually less than the required threshold to continue with the video playing. And in case the buffer is beyond a certain level, we are just giving it a very small positive reward. But by giving this a very high negative reward in case of falling below the buffer, the agent is learning sufficiently well that it needs to keep the video buffers full at all times. So, here this is what our micro app receives in terms of the states, that is the CQI and the backlog buffer which comes from the RAN environment, and the application state which is the media buffer length which is pulled in from the video server themselves. So, the action again is the scheduling waits sent back to the MAC. What we get with this is the plot on top is what we get with just a vanilla max wait scheduler which does not have any kind of application state integrated in its decision, and the plot below is our RL scheduler with application context integrated. We see that when the channel goes bad, there is often a time that our media buffer at the client goes below the minimum threshold that is needed to continue with the video streaming, continue with the playout of the video. Whereas our RL scheduler is able to recover from this drainage of the media buffer pretty quickly because it was trained with that reward. So, the main takeaway is that an application aware real time scheduler effectively reduces the rebuffering time and definitely increasing your quality of experience in this case for your video streaming application. The other one which was talked about was Windex, which is basically our priority based scheduler where we have all these different service classes. You have MMTC, MBB, XR, URLLC, all of them have different requirements on throughput and latency. So, each of these applications require a certain throughput and the latency guarantee to get a really good quality of experience. So, what in this case what we do is we compute a priority index for each of these UVs per slot, and based on the priorities we simply order them in decreasing order of priority, and the UV with the highest index for that particular slot is scheduled for that TTI. So, what is the key idea? The key idea is every application has its own requirement for latency and throughput, and we are trying to guarantee the best effort latency and throughput required to get a good quality of experience. And if you are trying to do it, it's basically a combinatorial optimization problem where the number, as we scale the number of users and the number of requirements for each of these users, it definitely becomes a very hard problem and it cannot scale. So, our approach was basically to decompose the priorities for each of the users to individual problems, so that we take the number of UVs, compute some get an index out of it, and simply schedule the one which has the highest index for that particular TTI. So, Windex learns the priorities of that depends on the network state. What do I mean by network state is basically the backlogs, channel qualities, and here TSLS means the time since it was last served, and that is what we take into account as latency. And the other input to the state is the violations basically, that is how much violation is the UVs with the current scheduling, what is the violation from the throughput that the UV wanted, and also what is the violation from the latency that the UV actually desires. So, this was our RL specifications, where our state includes the network states, that is CQI, backlog length, and the time since last service, and also the percentage violations in terms of latency and throughput. Our action is basically 0 or 1, that is all the UVs with action 0 does not get scheduled. The UV with the highest index gets the action 1, that's the only UV that got scheduled for that particular TTI. So, we train Windex networks for each of these service classes to learn how to get the relative priority index for each of these UVs. So, we have a Windex network for each service class, which includes the network state and the percentage violations of their application requirement. This is how we get the reward formulation, which is basically a complex convex combination of the throughput of the required service violations as well as the reward, which is in our case we take the throughput as the reward function. And finally, what the network learns is the Whittle indices of each of these specific service classes. So what is this Windex micro app? We finally get for each of the 4 service classes that we mentioned, we get Whittle indices corresponding to each of these classes, and at the end, and for each of the slot, we compute the index for each UE, and we choose the UE with the highest index, and that's the UE that actually gets scheduled for that particular time slot. This is the basic, again, this is all out. It might be out there soon. You again get metrics from the RAN using the EdgeRIC messenger. You update the state space with the violations. You compute the Whittle index for the UE. Then you get the action based on these indices, and then finally assign the weights based on the actions, and then finally send the weights back to the RAN. And these are some evaluations. That is, obviously with Windex we are able to achieve the least violations for all the service classes, both in terms of throughput and latency. Yeah, please get in touch to access any of the code base. This is all available. Thank you. Questions?
Oh, thank you. I appreciate it. We're a little cut for time.
Okay.
You're good?